Welcome to Solving Systems of Equations by Graphing. Use this video while taking notes, pause often to get your notes down, and every time the video arrives at a you try, pause and attempt the problem, press play when you're ready to see the solution along with the work. These are the topics we will be covering in this section. What is a system of equations? In this section, we'll be looking at systems of equations made up of two linear equations. What is a solution to a system of equations? A solution is any ordered pair that satisfies both equations. So let's look at that first system that we were talking about in the last slide. The solution is 4, 7. So how could we check that it's a solution? We would plug it in for x and y and see if we get a true statement. So we'd plug in 4 for x, 7 for y, for both equations, and in the first one we get 15, so that works. In the second one we get 5. Some linear systems do not have a solution and others have infinitely many solutions. We'll investigate that more in the special cases slides. Let's take a look at two examples. Determine whether the ordered pair 8, 5 is a solution to the following system. To be a solution, it needs to work for both equations. So labeling x and y, we'll plug it in. So 5 times 8 minus 4 times 5, do we get 20? So we get 40 minus 20. 20 does equal 20. Now the temptation is to say, yes, this is a solution and move on, but you always want to double check that it works for both equations. So 2 times x plus 1, does that equal 3 times y? So we get 16 plus 1, does that equal 15? Does 17 equal 15? No. So determine whether this is a solution, not a solution. We'll look at one more. It says check the solution algebraically. That means using your calculator, plugging it in. So they give us this graph. Now notice that the solution is where the two lines intersect, and that is at the point 5, 1. So we're going to check if 5, 1 works. Now we can see that it works graphically. They want us to check it algebraically. So we will see 5 plus 3 times 1. Does that give us 8? 5 plus 3, that one works. 2 times 5 minus 9, does that give us 1? 10 minus 9 gives us 1. There we go. You try the following examples on your own. Press play again when you're ready to see the solutions. Great, moving on. Methods to solve systems of equations. There are 3 methods: graphing, substitution, and elimination. In this slide series, we're going to look at graphing. So solving systems of equations graphically. There are 3 things that can happen when you graph two lines. They can intersect at one solution, which is what we're going to be talking about today. They could be parallel, meaning they'll never intersect. That is no solution. And when you graph one line, it could lay on top of the other line, and that would be infinitely many solutions or all real numbers. So how do we solve a system by graphing? Well, we graph each equation. If the lines intersect, where that intersection point is our answer. If they're parallel, no solution. If they're the same line, infinitely many solutions. We're going to do 3 examples together. Solve the following system by graphing. When I use two equations, I like to use 2 different colors to keep it straight. So I've got m equals negative 5 over 3. That's down to the right. If you're not sure how I'm doing this, you can go back to the slides on slope. And then 5 over negative 3, that's up and to the left. Our b is equal to 3, that's where we start. So we'll start where our y-intercept is 1, 2, 3, and from this point we'll count down 1, 2, 3, 4, 5, right 1, 2, 3. 1, 2, 3, 4, 5, 1, 2, 3. It's really important, 1, 2, 3, 4, can't go anymore, to get all the dots here. 1, 2, 3, 4, 5, 1, 2, 3, and that's all we can do. We're going to introduce that ruler again. Make sure you use a straight edge because one of these points is going to be our solution. Great. And now using a different color, I'm going to graph the other line just so I don't get them messed up. So m is equal to positive 1 over 3. That's up and to the right. Or both negative, both positive, both negative, down and to the left. Our b is equal to negative 3. That's where we're going to start. So we'll start at 1, 2, negative 3, and we'll go up 1, right 1, 2, 3. Boom. I have my solution. I'm going to circle it really big. That is the answer. I'm just going to graph a couple more dots. Up 1, right 1, 2, 3. And then I'm going to grab my ruler, connect those just to finish the graph. But the answer here is going to be 1, 2, 3. Negative 1, 2. It's always a good idea to double check that your solution works algebraically. So you can plug in your x here, see if you get the y value in your calculator, plug in the x here, see if you get the y value. It does check out. 2 more. Solve the following system of equations by graphing. So we've got m equals 4. Remember, we want it to be a fraction over 1 up and to the right. So that's going to be negative 4, negative 1, down and to the left. B is equal to 3. We're going to start at that 3, 1, 2, 3. We're going to go up 1, 2, 3, 4 to the right 1. 1, 2, 3, 4 to the right 1. Can't go any higher. Down 1, 2, 3, 4 to the left 1. 1, 2, 3, 4 to the left 1. 1, 2, 3, 4 to the left 1. Remember, you're going to want to get as many dots as you can. As many dots as you can so that you can really see the actual answer. Let's look at the next one. I like to put a coefficient of a 1. It helps me here when I go to the slope, negative 1 over 1. That's down and to the right. Or 1 over negative 1, that's up and to the left. The b is equal to negative 2. So we go down 1, 2 to start. And then we'll go down 1 to the right 1, down 1 to the right 1. Now I notice it's probably not going to intersect over here, so I go in the other direction, up 1, left 1. There it is, up 1, left 1. Grab your ruler. And so that's going to give us the ordered pair negative 1, negative 1. Let's check it in our calculator. So what I'm doing is for the first equation, we've got both of these are negative 1. So negative 1, does it equal 4 times negative 1 plus 3? Type it in and we see that it works. Negative 1, does it equal negative 1 times negative 1 minus 2? And it works, so that is our solution. One more together. So we are going to look at this first one. M is equal to negative 2 over 1. That's down and to the right. Or 2 over negative 1. That's up to the left. And our y-intercept is 2. Notice that I'm always graphing before I do any other work. I want to finish one whole equation before I do the other. Down 1, 2 to the right 1. Down 1, 2 to the right 1. Up 1, 2, left 1, 1, 2, left 1. I really want to get all these dots because one of those dots will be our answer choice. And we'll do the other color. M is equal. Now you might notice something. The slopes are the same. Maybe that doesn't matter. Maybe it does. Make a prediction here. What do you think is going to happen? 1, 2. When the slopes are the same. So I'm going to go down 1, 2 to the right 1. Down 1, 2 to the right 1. Down 1, 2 to the right 1. Let's go up 1, 2, left 1. 1, 2, left 1. What do we notice? Are we getting any intersection here? We are not. In fact, these lines will never cross. They are parallel, which means there is no solution. There is no point at which these two lines will cross. One way to know that is that parallel lines have the same slope. Okay, you're going to try the next three on your own. Press play when you're ready to see them. I do show all my work individually. Answer to number 1, number 2, and number 3. That concludes our solving systems of equations by graphing.